There are two flavors of mass on a spring problem. The easiest flavor, by far, is the horizontal case. And remember last day I told you, I promised you, we would always use a frictionless surface. This is the easiest case because the weight of the block is always being canceled by the table pushing up with the normal force. And so that means that when I look at Newton's second law, F net equals ma, remember, that's the one great equation of 205. That's the one equation to bring them all and in the darkness bind them. We all had that tattooed onto us, right? Okay. Now, in this case, if the weight force is balanced by the normal force up by the table, the net force is just the pull by the spring. Okay? And so I could rewrite this as the force by the spring is equal to ma. Okay, in the horizontal case. Now, if that spring, when it came from the factory, is exactly that long, if I attach this block to the spring and just set the block there, it's going to stay there. Because the spring is neither stretched nor compressed. And we call that equilibrium. The furthest distance we get away from equilibrium, the turnaround point, we call the amplitude. Okay, and so if I were to pull this block out this distance A and let go, this thing would go boing, 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 boing forever if we had a frictionless surface. It'd never stop. And it would be going not at all here. It has to stop to turn around. It would be going fastest there. The net force is equal to 0 when the spring is neither stretched nor compressed. And that's where the acceleration would also be 0. If I look at this turnaround point here and draw a free body diagram for the block, I've got the weight down, I've got the normal by the table up, they cancel, and I have the spring pushing. Now if I look at Hooke's law, I know how hard the spring is pushing. It's pushing with an amount K delta S. But at that turnaround, the delta S is equal to plus or minus S. Whoa, I did not say that. And if you say that I said that, I will deny it. Who are people going to believe? You or me? Yeah. It's plus or minus the capital A. Okay? Now, that means that the magnitude of the force, always a positive quantity, is going to be Ka. And it's going to be pointing back towards the equilibrium position. Now if I do the same thing over here, I'm going to get the same free body diagram, but the force by the spring will be pointing the opposite way. Okay, so what we find is that the acceleration is 0 at the location where the block is moving the fastest. And the acceleration is maximum at the place where the block is not moving at all. And that's the answer to that first problem that you solved for today's homework that we did not turn in. Check to see if your neighbor got that right. Okay, do a buddy check.
Because at that point, right after that point, the spring is going to push the off. A positive acceleration.
Okay. Now, the more difficult case, the messier case, is a case where you hang a spring from a support and then you attach the mass to the spring. That causes the spring to stretch until the pull by the spring can balance the weight of the block. And at that location it would just stay and not move. We call that the new equilibrium point. Okay? Now if I pull that down an extra distance A and then let go, this block is going to bounce above and below the equilibrium point the same amount. So I'm going to have capital A below that equilibrium and capital A above that equilibrium. Now if I look at my free body diagrams, my net force is 0 at the equilibrium. There's no acceleration. And that's because at that point, the weight of the block is balanced by the stretch of the spring. Now, if I look at one of the turnaround points, for example up there, the weight's still the same. You can't change that except through diet or exercise. But now, the spring is not stretched as much. And so I have a spring force less than the weight. And that gives me a net force down. Now it turns out, we can show mathematically, I'm not going to take the time to do it here, but that net force is going to be equal to Ka, where A is the distance from the equilibrium point to the turnaround point. So it would be this distance here. Just like in the horizontal case. Now, the same thing is true at this turnaround point. The weight's the same, but now the stretch of the spring is giving a spring force much greater than the weight, giving me a net force up. This would also be equal to Ka, where the A is this distance there. Okay? Now, I want you to realize that throughout this whole process, we're always just using that F net equals Ma over and over and over again. Okay? It's just complicated by the fact that in this problem, the F net is not just the spring force. In this problem, the weight is not canceled by the table pushing up. Now, because that brings in an extra complication, I'm going to make you a promise right here now. Okay? You ready for it? On the exam, on the problems where you're going to have to worry about how fast this thing's going when it's 2 centimeters away from equilibrium, I'm always going to do that on a horizontal surface, never on a vertical problem. Okay, that's my promise to you.